Hello students, and welcome to the final video of this lesson. In this video, we're going to be making connections between a function and its derivative, and then a function's derivative and its second derivative. We're also going to be looking at something called the second derivative test, which you've been working with, but how you can actually use it a little bit deeper to make connections between whether we have maximums or minimums. So let's get started. All right, so given the equation, we have g prime, and we want to find, okay, where is the function concave up and concave down? Again, we have no information on g. All we're given is the derivative, but we can make inferences, we can make conclusions about g of x based off of the second derivative. So let's start analyzing this, and let's start with our second derivative, okay? Now, I've already kind of worked this out, and I do know that this can get factored in the denominator, but I'm going to worry about that a little bit later just because I've already worked it out. I went down the rabbit hole, and I realized it's just a little bit simpler to leave it in polynomial form rather than factored form, so you don't have to worry about chain rules within quotient rules. So we do have a quotient here, so I am going to be using the quotient rule. And so I'm going to get x to the fourth plus 6x squared plus 9. The derivative of negative 12x is negative 12 minus negative 12x. So I'm just going to leave this as plus 12x times 4x cubed plus 12x plus 0, and then square that denominator. So x to the fourth plus 6x squared plus 9, and then square that. Okay, so now I want to, that's the second derivative, right? But you want to go through the effort to actually simplify all these things, okay? So let's fast forward a little bit here. All right, so we have essentially just fast forwarded to this portion up above me, and we do know that we end up with 36 times x plus 1 times x minus 1 on x squared plus 3 to the third power. So hopefully you kind of just worked it out through there after we took that derivative and you went through all those algebraic steps of distribution, arithmetic of just combining like terms, and then factoring out things as needed. So now what I'm going to do is, of course, we're going to make our handy dandy sign chart. And what are our zeros? Where are the points where it's undefined? So we have zeros at -1 and +1. One thing I was thinking about the first time I was doing this problem was, why don't we get like the square root of 3 as in the denominator? Well, if you take that denominator, you set that equal to 0, you're going to find that there are no points, no values of x that actually complete that to be equal to 0, because whenever you square something, it's always going to be positive. When we add that to 3, it's always going to remain positive. So no matter what happens in that denominator, it's always going to be a positive value. So we actually don't get any points where it's undefined. So we do get only -1 and +1. And we're going to want to use those values in order to complete our sign chart. So we're always going to get positive 36 in the numerator. So if I choose values less than -1, all right, so there's my division sign right there. I'm going to get a negative, and then positive in my denominator. So all this becomes positive. And I just want to make a note that this is the second derivative. Values between -1 and 1, let's use a 0. So I'm going to get a positive 36. I'm not even going to worry about that. And then 0 plus 1, that's going to be positive. 0 minus 1, that's negative. And then positive in my denominator. So this all becomes negative. And then one more time, my second derivative again. I'm going to get positive 36. And then let's go with like 5 or something. So 5 plus 1. I'm going to get positive. 5 minus 1 is positive. And then in my denominator, 5 squared plus 3 cubed is positive. So all that becomes positive. Well, what are the inferences? What are the conclusions that I can make? Well, the first thing that I can say here is that g of x is, because we want to talk about what is the concavity of g, and we're going to make our conclusions based off of, oops, I wrote f prime right there, g double prime. But what are the conclusions that we're going to make about g of x based off of the second derivative? And so g of x is concave up on negative infinity to negative 1 union 1 comma infinity. And we know this because the second derivative of x is greater than 0. And then along with this, we know that g of x is concave down. And we know this because, we know it's concave down on negative 1 to 1 in between those two values, because the second derivative of x, the second derivative, is less than 0. It is negative. And again, we see that in our sign chart above right there. And then finally, we have points of inflection. So we're going to say g of x has a point of inflection at x equals negative 1 and x equals positive 1. We know that points of inflections exist when those are x values are true. And we know this because the second derivative of x changes signs. And again, you don't need to specify whether it's changing from positive to negative or negative to positive. Only the fact that it changes signs is enough to state that those are points of inflection. And I want to give you a bit of a foreshadowing about one of the things that is really imperative to do is be able to take this information and sketch a graph of g of x, or take the information and sketch a graph of g prime, or the second derivative. And it doesn't need to be accurate, but based off of all this information, you know it's concave up, you know we have points of inflection, you know where it's increasing or decreasing if we were to do those sign charts for g prime. So you'd be able to make those conclusions and draw a roughly accurate graph of g of x without actually knowing what that original function was. And with that, we'll actually be able to use that a little bit deeper, called the second derivative test. So it's usually used to determine intervals of concavity, points of inflection, things like that. But we can also use it to find maximums and minimums, which is going to be useful in the case that the first derivative might be a little bit too difficult to work with, but it's easy to find that second derivative. All right, so there's several things to think about here. So remember, this is just another way that you can identify relative maximums and minimums. Normally this is going to come up in sort of multiple choice questions, but you can also use this definition as you answer free response questions as necessary. So what you want to think about is, all right, so let's assume that x equals a is a critical value of f of x. So we know that f prime of x is equal to 0, or it's undefined, right? So we know because it's equal to 0 or undefined, then we know that f of a has a potential maximum or minimum. Now we can go into the first derivative test and actually determine whether it's a maximum or minimum based off of it changing to positive to negative or negative to positive. But we can also go into it this way. So if we know x equals a is a critical value, and we know that the second derivative is greater than 0 at a, then we know it's concave up. And since it's concave up, right, we know that it has a minimum there because it's concave up, and so it's at the bottom of that point, so we know we have a relative minimum of f of x. Now again, if we know x equals a is the first derivative is equal to 0 or undefined, then we know we have a critical point. And that second derivative is negative, well, the second derivative means it's concave down, and if it's concave down there, we know that we have a point at the top, which makes it a relative maximum. Now, of course, if it's neither positive or negative, then we know that f of a has neither a max or minimum, even though it is equal to 0 undefined. Okay, so that's the second derivative test. You can use it as necessary, or you can just keep using the first derivative test. All right, but we're gonna go through a couple examples where we're gonna see how it can work here. All right, so we want to identify these relative extrema here, okay? Are they maximums or minimums? And so let's go through our first problem. All right, so we know f of x, so let's find f prime of x, right? And we know that it's going to be 4x cubed minus 12x squared plus 0. Okay, fantastic. What I also want to do over here is I want to find the second derivative of that. So then that's going to be 12x squared minus 24x. Okay, so I'm going to factor both of these here. So let's factor this. Let me see. So what I'll get is I'm going to get 4x squared, and then I'm going to get x minus 3 equals 0. So we know that x equals 0 and x equals 3. And so I'm going to actually factor this one over here as well for the second derivative. And we're going to say that, well, I can factor out a 12x, and I get x minus 2. And what I want to do, so f, the second derivative of f of x equals this. What I want to do is I want to find the second derivative at 0 and the second derivative at 3. So no sign charts here for the first derivative test. I just want to use that second derivative. So the second derivative at 0, and again, I'm pulling those from these two values there. So the second derivative at 0, that's going to be 12 times 0. And then I get 0 minus 2. And that's going to come out to be 0. And then let's look at the second derivative at 3. And so I'm going to get 12 times 3. And I'm going to get 3 minus 2. And so I'm going to get a positive number. So I'm just going to say that this is greater than 0. I don't really care about the exact value. Okay. Well, what are we going to say? Well, we know that x equals 0. Well, what are we going to say? Well, what we can say from this is that f of x does not have a relative max or min at x equals 0. And the reason we can say that is because the second derivative of 0 is equal to 0. Okay, so the second derivative of f at 0 is actually 0. It's neither concave up or concave down. So it's not a maximum or minimum. And in fact, if you graph this, you actually see that at that point exactly is a point of inflection, okay? And so it's not at the top of a hill, it's not at the bottom of a value, it's a point of inflection. And that's exactly what a point of inflection looks like. So then here, what will we say about at x equals 3? So we're gonna say f of x has a relative minimum at x equal to 3, and we know this because f prime is 0, so we've already done that work, but we know this because the second derivative at 3 is greater than 0. So that's the second derivative test. It's because we know that that first derivative is 0, so then we can say that the second derivative is only positive. It's all we need to state, which makes it concave up, and we have a minimum when it's concave up, don't we? All right, now we have our final problem here, and this one's going to use some trigonometry. So I have f of theta, so let's find f prime of theta. Well, then that's going to be -2 sine theta minus 1. And let's find that second derivative. So the second derivative of theta is going to be -2 cosine theta minus 0. Okay. So going back to that first derivative, we want to find, of course, on the interval from 0 to 2 pi, we want to find, all right, where are we having critical points? Where are those coming up? So we set this to equal to 0, -2 sine theta minus 1 equals 0. We add 1, we divide that by -2, so we know that sine of theta is going to be equal to -1/2, okay? So what values of theta do we get that make that true? Well, then that's going to be 7 pi over 6 or 11 pi over 6. We don't have to worry about any coterminal angles because it says on the interval, on the standard interval from 0 to 2 pi. So now when we're doing this work, we're checking 7 pi over 6 and 11 pi over 6 on that second derivative function. So let's find that second derivative of 7 pi over 6. So -2 cosine of 7 pi over 6. So 7 pi over 6. So cosine of 7 pi over 6. What do we get there? Well, that's going to be a negative value, and a negative times a negative 2 is going to be a positive. So we know that that comes out to be greater than 0. And then if we find that second derivative of 11 pi over 6, well, we're going to get negative 2 cosine of 11 pi over 6. And cosine of 11 pi over 6 is going to be a positive value. Positive times negative 2 is going to be negative. So all of this comes out to be less than 0. So what conclusions do we make about f? Well, we know that f of theta has a relative max at theta equals 11 pi over 6. We know this because that second derivative of 11 pi over 6 is less than 0. So it's concave down, which means you got a maximum that's at the top. So that's why we have the relative maximum. You want to think concave down, that doesn't mean you have a minimum, right? So you want to think about exactly what do these things mean. And then along with this, we know that f of theta has a relative minimum at theta equals 7 pi over 6. We know this because that second derivative at 7 pi over 6 is less than 0. Again, sorry, not less than 0, greater than 0. There we go. And again, we know this because we know that if it's concave up, that we have a minimum. It's at the bottom of a point there. It's at the bottom of the valley. All right. So the biggest tips I have for this are really pay attention to what concave up and concave down mean, okay? Because that's going to be the most imperative part to getting through this lesson. Of course, if you do need any help with this video or any of the previous videos, or if you're struggling with some of the mathematical analysis concepts that we're talking about points of concavity, points of inflection, concave up, concave down, if you're struggling with what those mean, I encourage you to graph some of these examples and look at how the graph changes and twists over time at these x values, okay? But of course, if that still doesn't help you, you can always reach out to me. I'm Mr. Hernandez, and this was Mr. Hernandez Teaches.